Yes.
Okay.
Yes, so thanks for the invite first. And so I'm going to talk about this work that we presented this year at CIR. And, it's about click modeling, which is kind of a niche topic in IR. So I will really explain, the setup, what we are really trying to achieve, and so on. And we are concerned here with the evaluation of click models. So we introduce metric, but first I will need to introduce a concept which we add to a paper, which is called Debiasedness, and then actually it's metric to measure this debiasedness. So it's a joint work with these people here, and well, let's start. So this is the setup. So you have a data set with rankings and corresponding clicks, and you would like to learn from this data set. The problem is, if you just learn naively from the clicks, so you typically say something like, oh, the relevance probability of a document should be equal to the click probability of a document, you are probably completely off. And this is because there is bias in the data set. I think most of us know that. For example, position bias is the fact that the items on top are usually more likely to be observed, and therefore they're also more likely to be clicked. So in this example, the third item is the most relevant, and yet it's not the most clicked because it has a lower probability of observation. So we need to counter this bias. And click modeling is the idea that we are going to learn from data what are those biases, and hopefully you can get to the true relevance probability. So the way we are going to do that is by learning the causal influence of every parameter that can have an impact on the click probability. So notably the relevance of the document and all the presentation, like the bias factors that come from the presentation of the results. And the idea is to have a model that is constrained in its architecture in a way that encodes assumptions about the user behavior. So we first formulate an assumption, and then we implement a model that encodes this assumption, and we train it normally with maximum likelihood estimation on the clicks. So this is the example of the PBM, the position-based model. It's probably the simplest one out there, I think. And basically it states that to be clicked, a document should be first observed by the user, and then the user must find it relevant. And only then it can be clicked. So you end up with these two branches, the observation branch and the relevance branch. So both of these could be, for example, neural networks, or any model of your preference. And the output of this would be a latent variable. So there is the probability of relevance on one side and the probability of observation on the other side. And the position-based model also states that this probability of observation depends only on the position. And the fact that you have different inputs to this different branch gives you confidence that what you learn is actually the true value of the relevance probability and the observation probability. So that sounds like a plan, but we have a problem because we made an assumption on the user behavior, but we have no idea whether it's actually the right assumption. So in a more realistic scenario, what we might want to do is to train a lot of these models with different assumptions about the user every time. And then we want to have a criterion to select the best one, the one that we are going to use in deployment. And so this is where evaluation comes in. But just before I talk about the different ways of evaluating, I'd like to take a step back and think about why we do that. So usually we have a target task, a downstream task, which could be simply training a better policy with policy training and evaluation, and counterfactual learning to rank, and so on. It could be a different kind of policy, for example, with reinforcement learning, or, and I think you are interested in that, it could be fairness of exposure. In that case, you need like a very good estimation of the relevance probability and also the bias, like the position bias, to be able to give a fair exposure to every item. The thing that is common to all of these tasks is that they require some kind of out of distribution click prediction, because by definition, what you are doing is you are training a new policy, which is going to be something different. And therefore you need like your predictions of both the latent variables and the final click prediction to also hold with this new policy and this new bias. So yeah, the model needs to be able to predict the click outside of its training distribution. But now if we look at the evaluation protocol that exists, the first one is in-distribution click prediction. So it's in distribution because you take your data set, you split it randomly into train and test, and then you just use a binary classification metric like log likelihood, for example, to measure the goodness of fit of the model. So on one hand, it's good because we want a model that fits the data well, but it does not tell you the full story, and it does not tell you anything about the out-of-distribution capability of the model. So that's why we have a second protocol, which is relevance estimation, where we ask some human experts to annotate documents. And then we can compare the ordering that the human experts produced with the ordering that the click model produced. And you can just use NDCG, for example, to quantify this. So this is good because we measure directly the quality of this latent variable, the relevance score that the model learns. But of course, it has some limitations. For example, it's only about the relevance, but there could be like many different latent variables, and maybe we want all of them to be estimated correctly. Also, you could have some issues with label noise and annotator disagreement and so on. But that's not the main issue. The main issue is that if you just have these two criteria, you cannot detect all of the residual bias, and so you will have a problem on the downstream task. So this is the same example, still with position bias, but here I have ordered the documents by decreasing amount of relevance. So the first one now, it is favored both by the relevance probability and by the observation probability, which means it has a very high click probability. Now, if you train a naive model, so it just says, click probability equals relevance probability, you can see it has the right ordering, which means that it has an NDCG of 1. So it sounds like it's a perfect model, even though it is clearly not, because it does not account for position bias. And indeed, now if I reverse the ranking, so it's outside of the training distribution, you can see that the click prediction is completely off. So, well, what's going on? So this is where we introduce the concept of debiasedness. So it's the idea that the relevance scores predicted by the model should not be influenced by where the logging policy placed the document in the data. If there is still a correlation between where the document was placed in the data and the model prediction, it means that there is still bias that has been transferred from the logging policy to the model. Actually, there is an analogy that I like. Let's say you are a teacher at school and you want to spot a cheater. If you just look at the grade, you cannot spot the cheater, right? Because then they could just have copied on the classmate, and if the classmate is good, they get also grade. Actually, you can even be better than the classmates, if they combine what they know and what the classmate knows, and so they can even have a better grade than the one who is not cheating. So you cannot do that. What you have to do is to compare the mistakes. If like two students make the same mistakes every time, then there is definitely something fishy going on. And this is exactly the idea here. If every time the logging policy was suboptimal, the click model also makes the same mistake, then there is something wrong. And so it means that it has not debiased the data in that sense. So this is why we call it debiasedness. So yeah, mathematically speaking, that is a conditional independence relationship, which I've written here. And we can test for it using conditional mutual information. I'm not going to explain how it is computed in practice. It's in the paper if you're interested in it. But yeah, basically conditional mutual information is something that is 0 if there is complete conditional independence, and it's more than 0 if there is not. And it's kind of a way of quantifying how correlated two things are. So here we want to make sure that the relevance scores predicted by the logging policy, or relevance scores that we estimate that the logging policy predicts, are completely independent to the scores predicted by the model, conditionally on the true relevance scores given by the annotators. And yeah, this is kind of a visual overview of it. So here we trained two different models. On the top row, this is the DCTR model. So it's a naive model that does not account at all for position bias. And at the bottom is the PBM, which accounts for position bias, and in this case is the correct model. And what you can see is that the NDCGs are the same. Actually, the naive model is slightly better, even though we know it's clearly a nonsense model. But if you look like the CMIP, well, we can see that there is still a very strong remaining correlation for the naive model, whereas the PBM has completely removed the bias. And we can see visually, so let's say you look at, for example, column number 3 here. There is clearly an upward trend between the model prediction on the y-axis and the logging policy prediction on the x-axis. So there is still this correlation. And if you look at the PBM, so it makes mistakes, because, I mean, we trained it with a neural network and so on, so it's not perfectly estimated, but at least the mistakes are not correlated with the logging policy. So then we can say it is debiased. Also, you can see here that, being debiased is not enough, because a random model, for example, is completely uncorrelated with the logging policy, and yet it's a random model, so it's bad. So you need both debiasedness and kind of quality of the orderings. And so if you have at the same time a high NDCG and a low CMIP, then you know that you have a very good model. Yeah, so in the paper we of course have a more rigorous analysis of this metric. So we tried just a lot of different experiments with many types of users, many logging policies, and many target policies that are a policy we would like to evaluate. And what we show is that CMIP, this metric, is actually predictive of the out-of-distribution performance, which is what we were interested in the first place. We also show that, let's say you are a practitioner and you do exactly as I said in the beginning of the presentation. So you train a lot of models, and then you select the best one according to your criterion. Well, then if you include CMIP in your selection rule, you get a lower regret. So yeah, basically you deploy a better model. So it's not directly like an evaluation on the final task, which would be, for example, fairness, but at least we show that it has completely, removed the bias, and so it should also be quite good on this final task. Actually, I can have a word about this. Whether it is like reinforcement learning or fairness, these tasks are actually super demanding for a click model. The thing is, there is an optimization going on, which means that if you have inaccuracies in your model, they will be exploited by the optimization process. In reinforcement learning or bandits, it's an unconstrained optimization. In fairness, it's usually constrained, but they're the same thing. And this is called the optimizer's curse. So any inaccuracy of a model will be used by the optimization algorithm, which means that you really need a model that has very good accuracy. So yeah, I think that's kind of like the natural next step. It's to now make sure that we can actually recover good fair policies or reinforcement learning policies. All right, so maybe just a summary of what I said. So there is a residual bias that kind of flies under the radar with the current evaluation protocol, with these like 2 different ways of doing it. This metric, CMIP, it's able to detect this bias, and so it makes the whole thing more reliable. You can actually count more on your offline results before going online. And, of course, it has some limitations. So like so first, yeah, it is not self-sufficient. You have to add it to the NDCG. You cannot just use CMIP. Right now, it's only pointwise, even though we could also imagine to have pairwise or listwise extensions, but right now it's only pointwise. And yeah, it does not evaluate the estimation of other latent variables. It's only the relevance. Most of the time, this is what we are interested in, but not always. And, let's say, for example, you have many different bias factors, not only the position, but also the neighboring items and the previous clicks and so on. Then you actually have to make sure that every one of these latent variables, like for example, the probability of clicking on an item after having clicked on another one, this type of things, you need to make sure that they are correctly estimated. Still, we could use kind of like the same strategy, but that's not what we do in this paper. So this is a QR code to the paper, and I think we can have a first round of questions, maybe.
Yeah, sounds good. Thank you so much for your presentation. I think normally we stop the recordings for the question and answer, but since we have more time, I mean, I'm happy to keep it on if you'd like.
Yeah.
I'm not super familiar with click models, so I guess my question is, if I understood correctly, the premise of this is that your click model becomes a reward function for some kind of reinforcement learning algorithm. So the premise of what you're saying is that if this click model is inaccurate or has biases, then these will be perpetuated in the reinforcement learning algorithm.
Yes, that's exactly it. And whether it is just counterfactual learning to rank that you're doing, or reinforcement learning, or fairness, you still have the same problem. You're going to do some kind of planning inside this model, and so if it's inaccurate, of course it's bad, and especially if it is biased.
And so if I understood correctly, then CMIPS is essentially a metric of how sensitive your model is to the position, like how sensitive your model's relevance predictions are to the position in which it was presented in the data set.
Yeah, I mean, it's more like a quantification of how well it has removed this bias that comes from. So I say position, in the presentation, but it's more of an example. Actually, it could be many different things. And in our experiments, we have more complex models. I think I have it somewhere. Yeah, I have it here. So we came up with a few more complex models to see what happens when you train the wrong models. Like, for example, we have this mixture Debian model. So I'm not going to explain, but it's kind of a complicated user behavior model. And we can train a lot of models that do not fulfill these assumptions. So they are all wrong. We know that. But the question is, which one is the least wrong? And then in that case, CMIP would be just a quantification of how well each one of these models has removed the bias from the data.
I guess my follow-up question to this is, isn't the premise of a user model to mimic the performance of like how a user would interact with a platform, and in that sense, humans are sensitive to position bias.
Yeah, sure. I mean, well, to be honest, actually, what we say here is that we really just look at the performance on the downstream task. You could have the wrong model, as long as it's able to give you what you want in the end, we are fine with it. So it's kind of a different approach. But I mean, yeah, I agree with you. Of course, we want a model that is able to explain what's going on, and it would be a more general model. So yeah, then that's definitely the point here.
I see. So if I understand correctly, then I guess it's more of the idea of your model as a relevance estimator, to have a more accurate and less kind of biased relevance estimator, than rather like a concrete simulation of like a user as they would interact with.
Yeah, we're not claiming that we are like modeling the human mind or anything. It's a bit ambitious. We are just saying, if we want to learn from data, well, we need to kind of remove this bias that is present in the data, because otherwise we're going to just replicate this bias, and the resulting policy is going to be bad. And so, yeah, it's okay to have a model that underfits the human behavior, as long as it does not give you crazy predictions. Very simple example of this. If you take the PBM here, so I said an item is clicked only if it is observed and then found relevant. But we all sometimes misclick on an item, so we do not observe it, and yet we click on it. Actually, this is not a big deal, because it just adds noise, but it does not add bias. So we are fine with this model, even if there is, a misclick. Yeah.
Yeah, I think that makes sense. I open the floor. Do other people have questions?
I use them so far so good. So I don't have no questions.
I think I have more. My other question would be, do you think that this metric could be used as a regularizer in some sense? Because it looks like the Kullback-Leibler divergence.
Yes, I mean, definitely. That's of course the first thing I like. That was definitely the future work for me when we published that paper, trying to go to, I mean, use the same idea but for training, not for evaluation. So the thing is here we use the annotations to kind of anchor this metric into reality. During training, we would not have the annotations. So we would need to find some kind of proxy or something, which is kind of dangerous. But yeah, at least it is certain that you can have information just by looking at the distribution of the predictions. Like just look, if you just plot your predictions or model predictions, you can have actually a pretty good idea of what the model is doing. And I actually don't know what would be the the best way of doing that, but there is certainly ways to say, okay, here there is something wrong, so we should skew the distribution in a different way. And I don't know if that makes sense. It's maybe a bit abstract like that, but
no, it does. It does. It makes sense. Awesome. I don't think I have any more questions.
Yeah, then let's
Yeah,
stay.
seems like there's no more questions. Thank you so much for presenting again. Look forward to hearing more about the future works. And yeah, thank you so much.
Thanks a lot. I guess I will stop recording.